Hello, everybody. This is our last video in which we talk about inferential analysis. And we've talked about a whole bunch of concepts so far, talking about simple linear regression and the assumptions underlying carrying out regression. We've built upon that and talked about confounders and how stratification in multiple linear regression can help you account for these additional predictor variables. In this final one, we're going to tie it all together, talking about other approaches that are built on regression, such as t-tests and correlation. We're going to discuss this sentiment that people throw out into the world that correlation is not causation and dial down as to what that means. I'm going to talk a little bit about multiple linear regression and visualizing it to make sure that we get a deeper understanding about exactly what's going on when we add additional predictor variables. So with that, we are in the 0507 Beyond Regression notebook. And the first thing I wanted to talk about here was the idea of correlation. So there are different ways in which you can measure correlation. Most of the time when people are talking about correlation and don't add any modifier, they're talking about Pearson correlation or little r correlation. And this measures the strength of association between two variables. Pearson correlation takes the values between -1 and 1 inclusive, where you can have different levels of correlation and in different directions. So positive correlation, which you probably have some intuition about, occurs when r is greater than 0. And as r approaches 1, x and y are highly correlated. So what I'm doing here is generating some random data and then plotting that, or showing the array of the correlation. So there is a core coefficient function from NumPy that will give you the correlation between x and y in an array. So x and y are your rows and your columns, where 0.815 shows you the correlation between x and y. The correlation between something and itself will always be 1, and that's what you see on the diagonal. If we want to visualize these data that I just generated in the x and the y variable, we can use Seaborn to create a scatter plot. And here we see what visually a correlation of 0.81 looks like. So the R value for the relationship between x and y here is 0.81. You can see that they are not perfectly on a line, but they're pretty close. You can envision a line going through these, and all the points are pretty close to it. Negative correlation, on the other hand, has a value less than 0. And as r approaches -1, x and y are highly negatively correlated. So going through that same process here, generating some data. Here, the negative correlation is -0.95. And when we plot these data, here we see a negative correlation of -0.95. So we can see this is a little tighter toward the center of that line than the last one. And it's in a negative direction. So as x increases, y decreases, indicated by that negative correlation value. The third possibility is when it is neither positive nor negative. When r approaches 0, x and y are not correlated. They don't really have a relationship. So here we see a number very close to 0. When we generate a plot from these data, you can see that there's not really any discernible linear pattern. We just have randomness across the middle. So if you were to try and draw a line through that, it would be a flat line. So this is what it would look like when you have no correlation between your variables. So I'm going to leave, again, the clicker questions in here because I think they're helpful. Feel free to pause if I don't give you long enough to think about it. But if I were to generate these data and plot them, visually my question to you is, what would the correlation, the R value, the Pearson correlation be here? All right, and we can always test what the exact correlation coefficient between two values is. And we can see that this is a correlation R value of 0.83. So you should be able to visually look at this and determine that it is not 0 and it is not negative because it goes up and to the right. So we're now between D and E. And I don't think there is a requirement that you be able to look at this and know for sure this is 0.8, but as long as you pick D or E, you're on the right track. In fact, there have been many studies done in which people look at plots and try to determine their correlation, and visually we're not great at it. It's really dependent on how many plot points there are on the plot and how well we can discern it. Okay, so the answer here was E, but as long as you pick D or E, you're on the right track. Now, here is a bit of a reminder. Putting this back to simple linear regression, where we had outcome equals beta 0, the y-intercept, plus beta 1, the slope, times the predictor. Beta 1 and R are related, and they are approximately equal under the condition that the predictor and the outcome each have a standard deviation of 1. So that is a special case in which beta 1, this slope, and your Pearson correlation are going to be approximately equal. So to see visually what this means, again, I'm going to generate some random data, storing it in X and Y. And I'm going to look at these data. Notice that I generated these data with a standard deviation of 1. So it's going to suffice this condition, that both the predictor and the outcome have a standard deviation of 1. When we look at the scatter plot, there's maybe not a discernible pattern here, but we can still carry out regression, right? It's just not going to have a strong relationship where my outcome and my predictor are specified when I create my design matrices. I then carry out ordinary least squares regression using linear regression and look at the results. What we see here is that beta 1 is a negative 0.03. And I said that this value is going to be equal to R under the conditions that we have here. So let's look at visually what this looks like. That is a pretty flat line, but in a slightly negative direction, which is what 0.03 as the slope indicates. And here are the same data, just with a line over top of it. What we can do is then look at the beta coefficient from the model and the Pearson R, so the Pearson correlation of the relationship between X and Y. And when I print those values out, you can see that they are, in fact, approximately equal. So I don't want you to think of correlation as something completely separate from linear regression, but it's a special case where the beta 1, the slope, and your correlation will be the same or very close to the same when your standard deviation is 1. So these concepts are related. Now, looking back to this data set we have been looking at in previous videos, we're going to keep using this data set now. The question here is, what is most correlated with violent crime? So what do you think? This is just a hypothesis question. And then the way you can determine the answer to this is by carrying out the core function from Pandas on your data frame directly. This is something you'll do in an assignment, and I just want to be sure that everybody is aware of what this output looks like and how to interpret it. So you have your variables here, your different features in your data set that are all of the quantitative variables. Again, along the identity line, along the diagonal here, it's going to be 1 because teen birth correlation with teen birth is always going to be 1. So anything with itself, the correlation value of 1. And the question then is, what is most correlated with violent crime? So we can look to this violent crime column, and then we look for the value that is closest either to 1 or to -1, right? So a value of -1 has a very strong correlation. A value of 0.8 has a strong correlation, but -1 in that case would be more strongly correlated. It would just be in a negative direction. So here we're looking, and the highest value here is teenage birth rate, 15 to 17. So we would say that this variable, B, is the answer here, right? So we just look at the column we're interested in and then see which value is most correlated across the other variables. This is the model we have been doing previously in our analysis. So just returning to this idea of regression then. I wanted to point out that in this case, the standard deviation for our predictor and our outcome was not 1 for each of them. So our linear regression gave us a beta 1 of 1.93. Reminder, that comes from this coefficient column in the predictor column row, where correlation is 0.67 and R squared is 0.45. This is something we haven't really talked about over here yet, but R squared is something that's output from this model. So far, we've been talking about little r Pearson correlation. R squared here is the squared value of your Pearson correlation. So how do we interpret it? What does it mean? So R squared is what is in your outcome, that's summary. And then 0.67 is the square root of this value. Okay. So what is this R squared value? Well, first, it is, as I said, equal to little r squared. And the way you interpret this R squared is it is the percentage of the outcome variable of the thing you're interested in understanding, your dependent variable, that is explained by your, in this case, linear model. It's going to take a value between 0 and 1 or 0 and 100 if you put it on percent. So here, this 0.453 says that 45.3% of the variation in teen birth, our outcome, is explained by poverty percentage, our predictor. So when you want to know how much of the variance in your model is explained by your predictors, you can see here it's about 45%. So poverty percentage does not explain all of the variance we see in teen birth rate. We can say it explains about 45% of the variance we see in teen birth rate. Okay, so beta 1 is the slope of the line. A 1 unit increase in our predictor, we would expect a 1.93 unit increase in our outcome. For our R squared, this is how much of the variance in our outcome is explained by our predictor. What I'm doing here is, again, generating the model and adding our line to it. So this is something we have seen before. The underlying data, 45.3% of the variance seen in this outcome variable and what we see falling away from the line is explained by poverty percentage. 100% of the variance would be explained if all the points fell right along the line. So some amount less than 100% is going to be explained anytime you have points falling away from the line. Now that we reminded ourselves of the data and the simple linear regression model, we're going to delve a little deeper into talking about multiple linear regression. I showed an example in a previous video, but we're going to build on this concept here. So here we're going to visualize the relationship when we have more than one predictor, and then discuss how correlation coefficients, R squareds, fit into that. So what I'm looking at here is violent crime, which is the second predictor variable we included in our model when we did multiple linear regression before. But we didn't talk about the distribution of this variable. So here is the dist plot. So we have violent crime on the x-axis. And my question to you all, as you're thinking about this, is what is your interpretation of these data? Should we use these data in our regression model? And if we should, what made you come to that? If not, what should we do to be able to use this variable? So I'll give you a few seconds to think on that. Okay, so what should be going through your mind is you look at this variable, you look at the distribution, and if we want to use it in linear regression, it should be normally distributed. And we notice that it's kind of normally distributed, but we see that there is maybe this bimodality going on. We have some natural split here in our data where we maybe have low crime and high crime areas. So something we can do is use this split point and say everybody who falls into this category is low crime. Everybody here is high crime, where 0 is low crime and 1 is higher crime. So I'm creating a new column here, applying and then just using a lambda function to do so, a new column that is 0s and 1s. So we have this new column where it's 1 if it's a higher crime and 0 if it's lower crime. If we look at the distribution here, so now we have a categorical variable. We can look at teen birth rate by violence, and we can see visually that there is some relationship between high violent area states and low violent states when it comes to teen birth rate. So this is something we saw numerically in our multiple regression before, but we didn't look at the underlying distribution and didn't make this binary. So when you use this 0, 1. Sometimes people call this making dummy variables. Sometimes people call it one-hot encoding. But now we're going to use this variable violent, where it's either a 0 or 1, and add that into our regression model. So we still have our main predictor and our main outcome, but we've added this binary input variable to our regression model. When we look at the summary statistics here, we see that the coefficient of poverty percentage on teen birth is 1.3. So for every 1 unit increase in poverty percentage, we would expect teen birth rate to go up by 1.3. And now we see between a 0, a low violent, and a 1, a high violent, we would anticipate a 10.4 unit difference in teen birth rate, which we can see visually when we look at this plot. But how do we put all of these pieces together on a single plot? So we'll get to that in just a second, but we have to talk first about this column here, the adjusted R squared. So we talked about R squared as being the variance explained in the outcome by our model. So we are now with this new model explaining 60% of the variance, but there's also this adjusted R squared value. The one thing that's important to note is when you add an R squared value to your model, when you add a predictor to your model, so here we have 2 predictors, R squared is going to increase this value here every time. By definition, more variance will have to be explained as you add more predictors. What you want to start looking at when you're trying to compare across models is adjusted R squared. What this does is it adjusts the model for how many predictors you have, so you can compare the amount of variance explained between 2 different models regardless of whether or not they have the same number of predictors. So if you add predictors, R squared is going to increase. Adjusted R squared is what you want to use to compare between models. So when we had 1 predictor for poverty percentage, we were explaining 45% of the variance. The adjusted R squared for that model was 0.44. For 2 predictors, our R squared goes up. We're explaining more of the variance in the outcome with our model, and the adjusted R squared is 0.59. That is the value you would use to compare between models. So you are, in fact, you have a better model here with 2 predictors using the 0-1 binary violent and poverty percentage inputs. So even after adjusting for the fact that we're adding a second predictor, the second model does a better job explaining the variance in the outcome. Now, to visualize this concept, we can use a scatter plot here. So these are the underlying data we've been looking at the whole time: poverty percentage on the x-axis, teen birth rate on the y-axis. We can color these points by violent level. So we can see our zeros are the blue points, low violence. Our oranges are the high violence points. And we can then add our regression line to this model. And what we see when we have 2 predictors is that these, and one's a 0 and one's a 1, we have 2 parallel lines. One explains the relationship in the low violence, and the other one is shifted up where the y-intercept changes here. It explains the 1. So we have these 2 different groups explaining the relationship between these variables. This is explained by this equation that we see here, where we see this shift between 0 and 1 for violent, right? So if this number were 0, meaning it was low violent, this term would drop out. If it's 1, you would expect a 10.5 unit shift in teen birth rate, which is what this shift from the blue to the orange is. Okay, so with this conceptual understanding of multiple linear regression, talking about what correlation is, we now need to jump into cautions about correlation. So we've seen Anscombe's quartet before. And I just wanted to remind everybody that you can have the same descriptive statistics. And before I mentioned we hadn't talked about it, but these are all, all 4 of these have the same mean standard deviation. And now that we've talked about it, the same Pearson correlation coefficient. So these, despite not all having the similar relationship, they can all mathematically have the same Pearson correlation. So no one number is ever going to tell you all the information you need to know about the data. So you have to draw plots, you have to calculate statistics, you have to make sure you understand the distribution and have descriptive statistics along with it. That said, we often make these comments that correlation is not causation. And we want to here give you an example of what exactly that means. Correlation, which is what we've been measuring here and what we've been doing with inference, establishes and measures a relationship, but neither correlation nor linear regression can say that one variable causes the other. Here's an example of that. There is a whole website and a whole book about spurious correlations. What we're looking at here are 2 different distributions where we're looking over time at a line plot. The red line demonstrates the divorce rate in Maine. The black line demonstrates the per capita consumption of margarine. And you can see that these two values have a very high correlation. They have a very similar pattern, but there is nothing to say that divorce rate in Maine had any causal relationship with margarine. They just happen to have similar patterns. And the same thing, per capita consumption of margarine did not cause the divorce rate in Maine. Same idea here. Number of people who drowned by falling into a pool, highly correlated over time with the films Nicolas Cage appeared in. So these spurious correlations can exist in the world, and they have nothing to do with causation. Now that we have that warning of caution, the last thing I wanted to talk about here was when you want to carry out a test, looking for the difference in means between groups, a t-test is what you're going to want to look for. There are assumptions for this t-test. The data have to be continuous or numeric, normally distributed. They have to have a large enough sample size, which historically has meant above 25 or 30. So most data sets these days suffice for that. And there has to be equal variance between groups. The null here is that the mean in one group is equal to the mean in the other group. The alternative is that the means between groups are not the same. We can take a look at this visually, where if we break down by violent, we can see the average teen birth rate in the lower violence areas is lower than the value in the high violence areas, right? So we can use this idea of grouping by and calculating a summary statistic. But how do we statistically test whether or not these are different enough to be confident that X bar, the mean in the 0 group, is not equal to the mean in the 1 group? So here, violent teen birth rate is the same between groups, and our alternative is that it's not the same. So we've got group 1 and group 2. To carry out t-test, you would use the syntax here, specifying that you wanted to do a t-test. You get a t statistic here, and then a p-value. And in this case, this p-value is quite small. It's 0.60 and then a 1. It's a number very, very close to 0, letting you know, which makes sense with what we've seen, that these two averages are different between groups. So we can conclude that we reject the null in favor of the alternative. We would conclude that the mean teen birth rate is not the same between violent and less violent areas. So observing this difference due to random chance is very unlikely. So as I said, we reject the null in favor of the alternative hypothesis. All right, so we've gone through here. T-tests, I haven't shown the mathematical underpinnings, are also related to regression, just like correlation builds on regression. So it's this very deep area of literature when you're doing regression and inference that a lot of these build on top of one another. There are assumptions for each of these that have to be tested and met, but these are very powerful tests that allow you to answer interesting questions, establishing and measuring relationships. All right, with that, do not forget to take the Canvas quiz.